Hello everyone. Hello everyone in Bristol as well as online. Greetings from Austin, Texas. I'm Kris, and we'll be talking about Law of Demeter, a practical guide to loose coupling today. Hopefully you've been enjoying the conference so far, and hopefully this talk won't disappoint you, and we will have something exciting to talk about. If you're interested in asking questions, I'm really happy to take them. Please feel free to post them on the Discord channel in the Empire discussion. I'll try to look at them all the time. There will be time at the end. Tim will let you know about that to ask the questions directly as well. So hopefully that's exciting, and I guess we can start. So what we'll be talking about, as pointed out in the title, we'll talk about the loose coupling, which is, I think, very important concept in software engineering, which is kind of overlooked sometimes, and it's not always as pointed out as it should be if it comes to quality of the software. So we'll take a look why we would care about it. We'll discover what the loose coupling actually means, because it doesn't mean the same for everyone. And it doesn't mean that there are different techniques to achieve it. So we'll take a look into that. The main goal of this talk will be to introduce the Law of Demeter, which is one of the ways of achieving loosely coupled code. It's a very important law, which I think it's not very well known, and we'll see how actually it can influence how we write the code. In combination of Law of Demeter, we'll talk about also solid principles. Not all of them, but we'll take a look into single responsibility, which is kind of associated with the Law of Demeter a lot. We'll kind of dismiss quite a few of them, but we'll take a look into also dependency, inversion, and injection. And I think those three guide principles will be a great example of how to achieve a loosely coupled code in order to improve the software design and architecture of the code which we are writing. Obviously, we'll sum up at the end with potential learnings, what was good, what was bad. This code is very practical, so there will be a lot of examples about what is good, what is bad, about particular cases which we will be discussing. So hopefully that will be enjoyable and everyone will be able to learn something out of it and have as much enjoyment in listening and asking questions as I had preparing the talk. Some of the slides will have a dark blue background, and I think that's what I noticed while preparing and giving a talk before, that some things are more important than the others, and the dark blue background means that, in my personal opinion, it's something to remember, and something which I would like everyone to take out of the talk itself. So take a look into that. I would always try to point out that there are things regarded to that. So let's take a look into the motivation. I'll be talking about software design law, and in my opinion, there are two books which are very important for every software engineer to get handle on and read and always have around. One of them is the Clean Code from Robert Martin, also known as Uncle Bob, in which there's a saying about the only way to go fast is to go well. And what that means from the software design, it means that if you try to go a long term, if you're software architecture, you can't go and take shortcuts in order to achieve a good design and go fast in the long term. Meaning that you can, write the code for 6 minutes and debug for 6 hours, and that's not the goal of software design. So in this talk, in this practical talk, we'll talk about how not to go into debugging sessions for a long time, and so that the software can be implemented in reasonable fashion, pace, and with just enjoyment. The other book which we're talking about a bit as well is my favorite book about software design and good practices, which is the Pragmatic Programmer. And this book has this really important, in my opinion, saying, which we'll discuss a lot in that talk, because what is the essence of good design? And this book tries to describe that in a very good way, in my opinion, because there's no one way of achieving a good design. A good design depends on many factors, and it depends on how it will be approached in the end. And the rule, which we'll be going through that talk a lot, and we'll always come back to that. And I think what is really important to follow when designing the software and making call on daily basis is to follow that the good design is easier to change than the bad design, which is called also ETC as a shortcut. So when we follow that rule, we can achieve a good design at the end, much more likely than not. What I mean by that is the fact that it's often the case we have, good practices which we can follow. For example, like solid principles, Law of Demeter, we can all of them follow on daily basis, and they help a lot. But we can also overuse them, use them incorrectly. We'll take a look into a lot of examples where, for example, dependency injection might be not applied properly. So I think that's really important to keep in mind. And it's very difficult to make sometimes that call upfront because it's not obvious sometimes whether the choice which we are making will give us the design easier to change in the long term. Following some practices, like for example good naming, we can apply that to ETC very easily, because we know that the code is read 90% times more than it's been written. So if we follow the good names, the design in the long term will be easy to change for everyone who is trying to follow. So ETC. What about singular responsibility? If you have separate of concerns and smaller classes which have singular responsibilities, it will be much easier to change them in separation in the future than instead of having a good objects which are difficult to change and test. So we'll take a look into that into more details, but I think what is important, and that's why there's a blue background here, that the essence of good design is not really specified as, oh my gosh, if I just follow those rules, I'll be, sorted and everything will be fine. We'll take a look into why that sometimes is not the case, but also we'll look into good practices which we can follow on a daily basis in order to get the design which is easier to change. And a good design is easier to change than the bad design. So let's keep that in mind, because that would be the a very important principle during that talk. So I hope all of that makes sense so far. And let's begin. So when we look at the design on its own, I think there are a few factors that we have to really consider before we'll get into the practical part of the code. So there's a Franklin rule in software engineering which says that nothing is certain in software development except for bugs and constantly changing requirements. Therefore, the only way to go fast is to go well, because we know that the requirements will change. It will evolve the software while it's implementing it all the time. And, the requirements from the product owners will change constantly. And if you won't be able to approach it and implement those requirements quite quickly, the software will stale and we won't be able to meet the deadlines. Obviously, we'll have bugs as well. So if you won't be, diligent with testing and other good practices, we also will not achieve the long-term goal, which is going through that talk. So all in all, that will not give us the design which will be easier to change in the long term. I also believe that the design has to be scalable, because it's really easy to write an application which has 100 lines of code of Python, no tests, and simple script. There's no issues there. If you don't have users, we don't have to maintain it. It's one-off. But we won't be talking about things like that. Here we talk about the scalable software which is required to be long-lived and has large scale we can think of like 100,000 of lines of code plus. Therefore, not all practices might be useful. Like, for example, dependency injection frameworks are not very useful for hundreds of lines of code, but for 100,000 lines of code, there's an argument there where they might be useful, for example. So, yeah, that's the scale we're looking at, which we'll be discussing more in that talk. One of the most important things about the software is that it will be able to be tested and it will actually do what we want. I'm working for a high-frequency trading company, so it's easy to be the fastest, but it doesn't matter if you're not correct. So it's really important to be both, in a sense. You have to be fast, but you have to be correct, because otherwise you can be the fastest to get out of the market. So testability is really important. And also there are like so many industries where, testability is the key, like, medical industries or financial industries or anywhere where life matters. And basically any software is important to just work as desired, right? Because if the software doesn't work as desired and we want tested, our users will, and that's not the case where we want to be. And users depend on, the software. If we write a software for ourselves, we might be the end users, and that's fine. We will still complain that it doesn't work. But stakeholders depends on the application, and I would make a claim that there's no software which doesn't have any users. So if you don't test it, our users will. On top of that, it's a nice saying from Google. It's called Beyonce rule. If you like it, then you should put a test on it, which I think is also really important to follow when designing the software and on a daily basis. Because if you want to test our software, we can't guarantee that it works properly. And then, although we might be fast in the beginning, we'll lose in the long term. So I think that's super important from the design perspective to at least have those, to be flexible, to be scalable, and to be testable. So moving on to loosely coupled code. What is that? Like if you look into the ETC rule, that would mean that the loosely coupled code will be easier to change. And what does it mean? It does mean that in the long term, what we're writing won't be a hassle to change. So if you get a new requirement from product owner, we can imagine that case that we practice in Agile, and there's a new requirement coming, and then we try to put an estimate on it, and for some reason at the beginning everything was simple and the estimate were short and they were able to be accomplished. But after a while, everything seems to be not going in the right direction. And that's where we can notice that the design is not there anymore. And it's often the case that we didn't follow the good practices and our code is probably tightly coupled and really hard to change. Loosely coupled code might be identified quite easily by the fact that it's easier to change. And that might be observed in agile methodology by the fact that we can commit and deliver what we actually committed to. So if you have a sprint and we have stories to deliver, we can deliver them on a daily basis according to the team velocity. In this particular talk, we'll talk about how to achieve the loosely coupled code based on C++ examples. We'll follow the Law of Demeter, we'll follow the single responsibility principles, dependency, inversion principles, and we'll take a look into testability as well, and try to figure out where is the limit, how far we can go, and what would be a great example of doing the code the right way. So, the rule, keep it simple, stupid. It's often the case that that's what we want. It's, over-engineering is one of the factors why the ATC is not accomplished in the end, because one thing is like writing a code, not testing it, and just trying to push it forward, and then pay the price, pay the tax afterwards. On the other hand, we can go too much and over-engineer the fact of writing the code by introducing frameworks for a simple task, which in the end doesn't work very well and doesn't suit the needs. So there are quite a few of rules, and there is a it's called stupid in a sense rule, which is opposite of solid, and that's how it may be accomplished in C++. So if you have the ACCU talk, which is a simple class, there's nothing really special here. First thing which is weird about this method run. Well, you can notice here that it's always inline. That will be a premature optimization, because we cannot guarantee that it will be faster, better, or anything like that. It's just, the rule of the company, of the policy is that, all methods have to be inline because that's always faster. There's no such a thing like always. If it comes to performance, you have to always measure, and always measure in the end-to-end kind of environment, benchmark, because micro benchmarks may be misleading either way. And not giving the hint to the compiler that this method should be inline, it's often better if it comes to the performance on its own. So premature optimization is a bad thing, and you can see that all over the place where we try to use C++, right? We use C++ because it's performant, and inline, it's often more performant than not inline, and that's why we get the performance, right? But always inline, it's questionable, and that's one of the examples when the premature optimization is actually bad for the software design and the performance potentially as well. We just can't guarantee that it will be always faster, and why we would do that. On the other hand, that's the code which is unfortunately very common in the wild, and that's what we will try to decouple in a sense, because this code is really hard, and it's coupled and it's really hard to test, and it's not performant, and there's hardly anything good about it. If you take a look into it, what is so bad about it? First, we have a manager. What is a manager? It's like, what is the responsibility of a manager? It's probably a God object which has a lot of things, a lot of responsibilities. It's hard to test, and it's really difficult to figure out what it's supposed to do. And the name manager, it's kind of already saying that, well, it doesn't have one responsibility because we weren't able to put a right name on it. So we just, created a manager where we put everything. And what we put in? We put singletons, because singletons are, what they are. They are hard to test. They are hard to debug. They are slow as well, especially in C++, post C++ 11, there's a guarantee that, static variables will have the thread-safe access, which often means that there'll be a guard associated with the access of it. So it won't be performant. It will be really difficult to test, because how you fake the singletons? Unless you do some linking magic, you probably are out of luck. And this code is definitely not, TDD driven or anything like that, because you would never write stuff like that if you were thinking about testing that code, because otherwise you're shooting yourself in the foot with that design. So yeah, that's another problem with this code, and it's just one line. Look at that. It's really hard to test. It's also really coupled. Look at that. It's like we have these get speakers. We don't know how to get the speakers, what speakers we'll get. So yeah, it's coupled to that as well. And then notice that we have these multiple dots, which we'll get into closely in a second, because that's also making a problem with testing, because we have to fake everything of each dot in order to get to the final thing. So that makes everything difficult. And I would argue that this code is just terrible, and we should try to avoid it as much as possible. This is a perfect example of this stupid code. What about attendees? In that particular case, we'll have this duplication. We'll access manager again. We'll get attendees. We still, don't know what we'll get out of it, because they probably coupled as well. We follow the same rule. We're not dry here, meaning don't repeat yourself. It's another rule which is really, important to follow. We just copy pasted it and didn't achieve anything in the end from that perspective. And then, the speaker talks and the attendees ask. So that's a simple example which we start from, and we'll try to refactor in that talk into way better design, which will satisfy our requirements regarding testability, flexibility, and scalability. And we'll take a look into how to achieve that. So hopefully that makes sense, and it's kind of exciting. If you sum up, what is this keep it simple design? Is it flexible? Not really. It's tightly coupled. We can't, inject anything. We just get things out of it. You can imagine how we would instantiate that. It's like there is, manager get speakers, set speakers. It's really hard to see how that would work easily. And in the test, you would have to really do a lot of things to make it happen. And it's when you have singletons, testing is really hard, because one, if you are coupled to specific concrete types, that's really hard to fake. But the other thing is the fact that the tests will affect each other. So if you have one test, will change the global variable, and singletons is just global variables in that sense. Global variables are as bad as singletons regarding the testing. So the test will affect each other. So one test, the order may be important. You have to remember to clean it up, and that's not always, or actually I would argue, ever desirable from testing perspective. Definitely this code wouldn't be written with TDD approach, which is test-driven development or behavior-driven development, BDD. Regarding the singletons on its own, they're not necessarily bad. It's the fact that they're being used inside the logic is bad, because you can inject a singleton from dependency kind of inversion principle, and that's okay. You can, if the case is to get just one instance out of singleton, that's okay. It's just if you have the access to the singletons from within the business logic, that's where the problems are coming from. Obviously, this code will be hard to extend as well, because all of these, kind of stupid principles. Is it testable? We kind of said that already. It would be hard to fake the singleton and manager, because we can imagine that the manager requires multiple singletons, and which one have to be faked. If you don't use like interfaces or concepts, we would have to, and we don't inject anything by a template, it would be really hard. It's like the only way I can think of would be like changing the linking approach towards the singletons, of like decompile CDP files. It's just a mad approach, and what would that make? It would just slow us down in the long term, because it would be really hard to make that happen. So definitely we can do better. So what are the problems? The problems are the singleton, the tightly coupling, untestability, premature optimization, in-the-script naming, and duplication. And you can see where is that going. That's why it's often called stupid principles, instead of applying the solid principles, which would be an alternative. So, what we can do about it? One of the problems with this tightly coupling, which is also part of the ETC, which means the design which will be harder to change, is the problem with these multiple dots. Object 1, dot object 2, dot object 3, and so on. In our case, that is manager, dot instance, dot get speakers, dot get, dot. You can see where is that going. It's like the more dots you have, the harder it is to deal with that, because one, you have the singleton in the front, so that's problem already. You probably have a tightly coupled object, so you can't inject them easily. That's 2, and 3. You have to fake all objects via the split by the dot in order to get the final get with the data or objects which you actually want to test. So all of that is really difficult. Therefore, the setup for tests will be really difficult, and will slow us down. But this code is actually breaking the law. And the law is called the Law of Demeter. Notice the blue background, something to remember, because I think this law in software engineering is not really as notable as it's supposed to be. And it says that you should only talk to your immediate friends. Not maybe in real life, but in software design, that's kind of important. So what does it mean? And it's often during that code talk we'll have examples which are bad or good, and we aim for good always with thumbs up. So this code, as pointed before, is bad for many reasons, because it's hard to test, it's in the business logic, it's hard to it's even hard to read, right? It's not necessarily easy to follow. So what's so bad about it? As you pointed out, it's tightly coupled, impossible to test, really hard to extend and reuse, because we have to add things into all these layers. So how to fix it? It's like I think that's important part of all of that. How to fix that code? It's like my claim, and hopefully you agree with me, at least a bit, that this code is not desirable and it's not following the ETC rule, so in the long term it'll be hard to change. So, C++ software engineers are smart, and we can imagine the fix. Like, so it's all about the dots, right? The Law of Demeter says that you should talk only to your immediate friends, which if you translate that to the software engineering, the code, it means that you should have only one dot. So you inject everything up to the point where you can access the thing which you actually want, which helps you with loosely coupled design and testing, and everything is just easy to follow. So what we can do, as C++ software engineers, we have pointers. So instead of dots, we can do arrows. And then we have no issue, right? Because how many dots we have here? We have 0 dots. So it's even better than the law of Demeter, right? We solved it by changing to pointers. Well, that's not a fix. Law is strict about the dots, but not in that sense. Yet another fix, which potentially might come into life when they're designing that software, is the fact that what about if we have a 1 dot per line? Well, all in all, it's still the same. It doesn't change the outcome that we still have a singleton, we still are tightly coupled, and we still have multiple dots. So that's not a fix for the law of Demeter, and this code is still as coupled and it's still as bad as before. I would even claim that the pointers are probably even worse, because I notice here that we don't even understand the ownership of that, who is responsible to release that pointer, that data. So yeah, that's not the improvement. The bottom part, I can imagine that being an improvement on top of what we had before, but from the design perspective, it's still the same. So how to fix it? There are multiple ways of fixing it. One of them will be by applying solid principles the proper way, and we'll take a look into how to not apply them the proper way, which is very common. And in my opinion, the best way of approaching the software design in principle is just to follow test-driven development or behavior-driven development, meaning starting from the test. Because if you start from the test and you feel the pain of trying to fake all of that up front, you'll make a code which is easy to test, because that's what will follow through. And that will make arguably the testable design, which is a good design in my opinion, because the good design is easier to change in the future. And if you can easily change the tests and be confident about the software, that's always good and positive for the future. So if you compare about solid and stupid, what we'll be talking about. So from the solid principles, there are quite a few of them. We won't be talking about all of them, but we will definitely look at the singular responsibility, because I think that's the most important, and also dependency inversion, and also combined with the dependency injection. I believe that those two give us the most out of the law of Demeter approach, because they allow us to inject interfaces which are single responsible, which follow the single responsibility. As pointed out before, following singletons, tightly coupling, untestability, premature optimization, bad naming, and duplications is not the way to go for the software design, but I hope that's kind of obvious, and we obviously don't want to follow that. So let's try to fix it. We were talking about everything what is bad so far. Let's try to make an improvement towards this ACCU talk, which we were so negative about. So the first thing which we can improve is to apply the singular responsibility principle. And if you take a look into what it is, although Swiss knives are awesome, not in software design though. Just because you can doesn't mean you should. In software engineering, having a Swift kind of knife approach when you have a God object, which you can't, like a manager, we were talking about this one, where you cannot, even put a good name on it, because you don't know what it's actually doing, why it's doing that, why it's definitely doing too much. And that will make everything difficult for us for the future. So let's try to avoid it. A class should have only one reason to change, and that's very easy to follow from design perspective. If you have a manager, what's the reason to change it? It's not definitely one reason, because it's affecting speakers and attendees. So it's already more than one reason. It would be better if you have speakers and attendees as a separate objects which we can actually talk about, and manager just goes away and we inject speakers and attendees instead. But we'll take a look into that. So how we can achieve singular responsibility principle in the ACCU talk which we are talking about. So just to point out, single responsibility doesn't mean that the code won't be coupled at all. It means that it will have single responsibility, but we can still screw it up. So in that case, for example, when we have the speaker, the name is still coupled to the speaker itself. That's one of the examples where we often mistake by the fact that, well, I followed the responsibility, single responsibility, but I still didn't think about other principles to follow. So in order to get the good design and the etc part of it, we have to make cautious choices which affect multiple things. Good design is contagious, but bad design is also contagious in a bad way. So the speaker on its own would have the responsibility to give a talk, and the attendee, also coupled in that case with the names, will have the ask questions responsibility. So from the single responsibility perspective, that makes total sense because it will be easy to test, right? We can create a speaker, we can test it. Although it will be coupled, we can, it's still an improvement over the design which we had so far. And the ACCU talk itself will have the speakers and attendees as member variables in that case. Notice here that it will be still coupled, so we'll follow through how to get that better. But that's the way of approaching the single responsibility and still being tightly coupled to the implementation. But it's a step in the right direction because the speakers and attendees can be at least separated and they have separate concerns regarding them. So if you look at the run function, notice it's not always inline anymore as well. And we avoided singleton. We avoided manager. So we have less code and basically easier to read code, easier to follow, easier to change. So all in all, it's a step in the right direction, but we can't stop there because that's not good enough. From testing perspective, it's still difficult to test the attendees because they are coupled, speaker is coupled, and we would like to be able to change that because everything is not set in software design. So we'll get a new requirement at some point, and if we're not ready for them, we won't be able to easily fulfill the requirements. Obviously, we don't want to go too far as well. So the limit and positive and negatives depends on us, and don't know how to highlight this. How to say the most that the most important part is etc. Just follow the etc on daily basis because there's no one way of approaching it. You can screw up everything. So is this design flexible? It's better, but it's still coupled, so it's not ideal, right? It's okay, but it's better because we don't have this manager, we don't have other things which were coupled, we don't have singleton. From that perspective, it's better. But is it scalable? I would argue that it's not as much. A bit easier to change because we can change components in separation. So we have speakers and attendees. We don't have to change the global manager in order to change them. So you can imagine that we have translation units when we can change them and even save on the compilation time, for example. So that's a good also factor of whether our design is better or not, that we don't have to recompile everything. Unless we try to get the most performance out of it and we just use header or something like that. Sometimes LTO may help as a declaration. Anyway, moving to testability of that design, it's a bit better, but it's still coupled, right? We can't inject different types of speakers, different types of attendees. Attendees and speakers are coupled, so better, but still hard. So what's the learning out of that? I think we kind of seen that having classes to have only one reason to change is an improvement over what we had so far. But we still have concerns, and one of them is the coupling. And the coupling is here quite bad, so that's not exactly following all the rules which we discovered here and talking about the law of Demeter, like one dot, that's great, but one dot is not enough if you can't inject other things. So what about dependency injection, inversion in that case? Because that's the way of how we can make another step forward towards a better design. And by not relying on the concrete types and implementations of those classes, we can inject them and be more flexible. And here, I think there are a few important things regarding dependency injection. One, it's a term which is often scary, but it's not. We'll discover why it's not. It's like I gave a talk about it some time ago that it's $25 concept for 5-cent term in a sense, because there's not much about it, and there are a lot of myths which we'll try to talk about here. One of them is the fact that you need a framework. Dependency injection doesn't rely on the framework at all. It might be done manually. Framework might be arguably beneficial in the large scale software development, but definitely not in small scale, and it's not required at all. And I think that's really important, and we'll have that on the slide at some point. The other thing which is also important, that dependency injection doesn't mean virtual interfaces. Achieving polymorphism and flexible design in C++ might be achieved in many different ways. Concepts, templates, functions, there are different ways of achieving the same thing. And virtual, which has positives and benefits, positives and negatives, sorry, especially regarding the performance and the inheritance on its own. It's kind of coupling. In that sense, it's not always the way to go, and just one way of achieving it. Good DI approach wouldn't be specific to anything. So yeah, as pointed out, DI is kind of scary sometimes, unless it's known. But what is DI most about? It's actually a design principle in which tries to achieve a way to reduce coupling. That's it. So it's a specific way that we inject objects into our classes in order to avoid the coupling. So if you have this example with manager and we have instance get, that's really difficult from the design perspective to test, as we pointed out, and it's coupled. Instead, we can inject speakers into the constructor, and that's it. That will be the dependency injection, which we'll talk briefly here. But if you look at it from really simple perspective, C++ constructor, the dependency injection, it's what about inject and how you inject? That's the other question which is opening here with the dependency inversion approach. But if you have constructors, we'll probably have dependency injection in place. But I think that's important. Whether DI is done right depends on what and how we'll pass into those constructors. Passing speakers which are coupled and we just copy them into member variable, that ain't gonna give us that much. And we'll take a look into that. So it's important to keep in mind that DI is a not scary term. It's all about the constructors, and it can be done properly or not. And what that means, we'll take a look in a second. And as pointed out, DI doesn't imply using a library or framework. And I think that's a myth we just commonly thought that, dependency injection is this scary thing and it requires, the scary frameworks. There are frameworks available, but it's not necessarily required. DI can be achieved without, and it's often the case for the smaller project that is actually better without. And it can be achieved in many different ways. It doesn't also imply virtual interfaces, it doesn't imply concepts, it doesn't imply templates, type erasure. All of them are options, not requirements for DI. As pointed out, DI libraries might help in the large scale. Because if you have a small project, DI on its own, DI framework may not be that helpful, where it's like, because you have a learning curve, you have to learn something, not everyone will like it, and it's, there are obviously this, 1% of cases where things are difficult, but in 99% cases it may help, and it may help with the fact that if you change the constructor parameters, order, or things like that, or like you change unique pointer to shared pointer, all of that, the ownership will be maintained by the DI, and it will be working out of the box without really changing all the code. So if you change the templates to virtual interfaces or vice versa, that's something which in the large scale framework can be useful for. But it's also really important not to couple to a framework as well, which is sometimes the case. So if you take a look into this example with the speaker, so far we had this tightly coupled code with the coupled name, and talk, ACCU talk, also coupled. So that's not great, better than before, but that's not great. Less coupling, the speaker can take the name in the constructor. Voila, we have the dependency injection, which is associated with the Law of Demeter as well, which we'll take a look in a second. So here, just to to be really clear about what is happening, we have a speaker which, the name, the data name here, we notice that we don't talk about interfaces yet, is being injected, and that's the only difference. That was coupled here because the name was coupled. Here it's passed by the constructor, and that's the only difference, and the data might be easily tested. So right now we can, if you have the method which requires the name, we can easily verify that it's actually happening correctly. So that's better because we can easily test it. So what about the ACCU talk? As pointed out, that's still coupled potentially, and that's a question which we have to answer ourselves. When we have the ACCU talk and we inject the speaker and attendees, although we can inject the data to the speaker and attendees, we still are kind of coupled. It's better, but notice that we cannot inject different types of speakers or different, things which satisfy the requirements for attendees and those speakers. But the speaker and attendees can be injected the data, so in that case, it's still okay. But we'll take a look into examples where that won't be sufficient enough. DI has this nice saying about that, don't call us, we'll call you. It's called the Hollywood principle, and that's where the injection coming from. Instead of having a get, like manager.instance.get, where you actually ask him, now you're saying, we'll call you, I will inject you who you can call. So hopefully that makes sense. There are obviously gotchas with all of that, because as everything, and I think that's important, outcome of this talk, which I would like to be proceed, is the fact that no matter what, everything might be screwed up in the long term. So even if we follow the rules, we apply DI. DI can be applied improperly, and that's what we will take a look into. So that we have constructor doesn't mean that we apply DI properly. it means that we have constructors. And we approach dependency injection, but whether we will do it correctly, let's take a look into some examples where we wouldn't do it correctly. So first one would be not using constructor consistently. So in that case, we have a speaker which is tightly coupled because, you know, we didn't, like, although speaker can be injected the name, ACCU talk, so we can verify the speaker on its own, that's fine, and we can test that. But the ACCU talk, instead of injecting speaker, it initializes speakers with the name, because that's what it does. And that's bad because, you know, the Kris is coupled to the speaker for the ACCU talk, which we cannot change. And if you get the new requirements for ACCU talk, that the speaker should be, you know, coming from the file or whatever, we won't be able to change that design. And it will be hard to test that design as well, because the ACCU talk will always be coupled to Kris. And I don't think everyone wants all the talks to be by Kris. So yeah, consider using constructor dependency injection consistently, meaning inject, if you start injecting, let's inject the things properly by following the rule of injecting things which we can follow the law of the matter in the fact that we'll have just one dot in the end. Because we can screw up that as well, which we'll take a look in a second. We can inject different things into ACCU talk, which will still ruin the approach. But when we look at the first line, coupling the Kris into the speaker is bad, but injecting the speaker is better. Not ideal, but still better. So, using singletons, yes, I'm complaining about them a lot because they're really hard to test. There are ways of achieving what we want with the singletons, but maybe let's take a look into that a bit later. What is important here is that the fact that using singletons makes everything harder, and using singletons with coupled name here, that's extremely hard to test, and because we cannot, you know, easily change that. So let's consider avoiding singletons unless we can inject them by the constructor. So you can imagine the case when we have a manager here, like the speaker. You can imagine that if you take it by a reference on the second line here, and you initialize with the singleton, when you have the wiring, that's fine, because ACCU talk will be able to be tested in isolation either way. And the production code, the injection will happen from the singleton, but that won't affect, the design of the specific classes. So that would be okay in that term. I hope that makes sense. But this code, when we have the singleton in the business logic, is just really hard to deal with, and we'll have to pay the tax for that. So let's try to avoid that. So that's bad, but injecting is good. And let's stick with the rule of let's just inject what we can as a rule of thumb. But what we inject is also important, and we can, as everything, screw that as well. We can have a leaky abstraction when we, instead of injecting the speaker in ACCU talk, we inject the name which the speaker requires. So that's bad because the speaker, we have a leaky abstraction here because the ACCU talk doesn't really require the name. Why we inject the name? We should inject the speaker because the speaker is required by ACCU talk. So that makes us having a leaky abstraction, which makes the design more difficult to test and follow. And it's very often a case in C++ that we have this particular case within the inheritance and CRTP pattern when we inherit from a derived class where we then propagate some parameters to some of the constructors of the derived classes. And that's bad from the design perspective, because we have a leaky abstraction, because the object which is required is not injected, and instead something which that object is required is injected. So we can imagine that ACCU talk would have 10 parameters, which is button and down, and 10 member variables, and some of them take some of other things, and some of them are just propagated to another downstream classes, and all of that is just messy design, which makes everything harder. Instead, we should consider passing objects which are initialized instead of passing the parameters to initialize them. I think that's a really important rule to follow, because it's very often the case, especially in C++, that it's so easy to make leaky abstractions in the code by not passing what is actually required, by passing the things which will be propagated to things which are required under the hood. So instead of passing the name for the speaker, that's bad, let's pass the speaker to the ACC talk, because that's much better. And that gives us the more loosely coupled design. We can follow the same rule. I was talking about the CRTP, and it's often the case, or mixins, like you can call them as well, that we do the same, the inheritance. Inheritance is bad on its own for different reasons. Maybe we'll not get into that too much. I'll just refer to the talk of Sean Parent about inheritance being a base class of evil. But the speaker here, it's is inherited, so we don't have the composition really well. We have inheritance. And the fact that we follow the same pattern as before, that we inject the name into the speaker, it's a bad idea as well. We have this leaky abstraction too, which makes the testing and, injecting things really hard. So prefer composition over inheritance once, and avoid leaky abstraction too. So that's bad, but instead of having a member, it's much better. We are talking about Law of Demeter, and that's the talk of this. That's the title of this talk. I think all of those things are really related to the loosely coupled code. So having Law of Demeter being applied properly is really important in the code, because singular responsibility plus Law of Demeter plus dependency injection gives us the ability to follow a good design, which will be testable. And if you apply test-driven development up front of that, we'll definitely get there. So what will be bad if we have the talk here, which we inject a manager. One is a manager, so it's already bad, but it's a talk manager, so it's a bit better. But the fact here is that the speaker is being initialized with manager dot dot dot. That's difficult to test, right? Why we wouldn't inject the speaker instead? One here is that's coupled. We have to, in order to test that, what do we have to do? We have to create the talk manager. We have to fake the get speakers for the Kris somehow. All of that is just difficult, and we have multiple dots, which means that we violate the Law of Demeter. And from the design perspective, that's bad, because it's just difficult to improve in the future. etc. It's not applied here because this design will be hard to change in the future. So yeah, let's consider talking to only our immediate friends in software development. So having multiple dots or arrows or whatever, it's bad, but injecting things which we want is a better approach towards the software development. And that's the Law of Demeter, so let's keep that in mind, that we would like to follow that. And Law of Demeter is important practice to think about when we design and write software. Yet another thing which we can do improperly is the fact that we can, in C++, getting a strong types is quite difficult because, we have to inherit from, especially for integral types, it's really difficult because we have to inherit from something and do like enum tricks. But getting them not being applied in our code makes things even worse. So what's wrong about this API? Well, I would argue that this API is really weak because we have two parameters for the speaker, first name and last name. Notice that the names are not important. We can say last name, first name, doesn't matter. It's two strings which you have to pass. So what does mean that if we look at this design and this part of code, when we inject, first name, last name, that's okay. But when we inject it in the other order, well, that's still okay, right? Because it doesn't, doesn't complain about it. If you didn't write the proper test for it, you wouldn't code it at all. And what is even worse, the fact that if you have the definition and declaration of the function, the names don't matter, so we can change them. We can say in the definition, in the header, last name, first name, both of them take string, and in the implementation, first name, last name, and all of that will still compile, and a developer who is looking at the header only to figure out the public API can be totally misled by the fact that the names are wrong. But everything will compile, and we should always prefer compilation failures when possible to avoid bad design. So strong types for strong interfaces, there is a really good talk about it from Jonathan. Idea here is that we have a named parameters, so that's the way we can achieve strong types in C++. Notice here we use C++20 NTTP, which is non-template type parameters for the second argument as a name, which is kind of handy. And in that case, this API is much better and it's considered to be a strong API because the first name and the last name cannot be mistaken. So first name Kris, last name Jusiak. If you mistake it and we put last name first or first name second, and we try to convert it from a string on constructor, all of that ain't gonna work, and we will get the compilation errors, meaning you didn't you didn't follow the interface correctly, so the API is not applied. So that's great. That will give us something better than subtle mistakes which we will have to debug for 6 hours. So consider using strong types is always good. So that's bad. Having two strings is bad. Having strong types is much better design. Another thing which is an improvement on top of that is the fact that we can combine parameters together. So if you have something which always goes together, instead of passing multiple things as a parameters, it's way better to combine them together because they have to go together. Like when you have the database, you have the path or user or whatever, password, all of that is combined together, and that's a better design. And if you apply the strong types on top of that for the specific things, that's even better. So in that case, following this requirement, when we have this imaginary function makeSpeaker, instead of having multiple parameters, even named strong type, it's less desired than just propagating one class with all the information which is required, because they can't go without it. Because on the first one, we can screw that up by, for example, last name will be a default or something like that, or the order is different. All of that makes it difficult. And with the makeSpeaker and the class with C++20, we can apply designated initializers, for example, and then we can say speakers info dot first name equals dot last name equals, and if that's a strong type, that will also give us the the ability to not to compile if you pass something wrong. So all of that is great. But we've been following quite a bit right now. We changed the code quite a bit and we discussed a lot of options, but this design is still not flexible. In order to make it flexible, let's try to approach it with dependency inversion principle. So the idea about the dependency injection is to depend on the abstraction, not the implementation. So far we always implemented it with the fact that speakers were speakers and attendees were attendees. We could inject the data for them, but we couldn't change, how the talk method behaves. So we can imagine that we have regular speaker, awesome speaker, keynote speaker, and they behave differently. The same with the attendees. And we cannot change that requirement if you would get it at the moment, because the only thing we can change is the fact that there are different names. So in order to do so, we would have to approach it with some sort of polymorphism. That's the way we can do it in C++. And there are different ways of doing that. One of them is inheritance with virtual classes. As pointed out when we talked about the dependency injection, that's one way of doing it, but that's not the only way. Another way is to apply type erasure. Unfortunately, C++20 or any C++ standard doesn't have any good library for that. There are obviously some in the wild, but there's no C++ support for it out of the box. So that's way of to approach it. Although in C++ we have like shared pointer or void is type erased. std function is a type erasure example, which has pros and cons if it comes to versus the inheritance. We can do std variant or std as well. Some of them have more of benefits than the others. Like variant is a closed set of things you can inject. Any, it's really bad with the performance and hard to follow the interface. So type erasure in that sense is better. Sometimes a variant of combination of closed types plus any at the end is a solution for being able to test. Maybe not the best, but one of them. Obviously templates. Template is a way of achieving the performance out of it. The code we have. Obviously they are contagious as well, so it's hard to stop them, which means that we have a lot of headers, compilation times are slower, but we gain the performance and we can actually get the inline right without the no inline. Concepts on top of templates are really, in my opinion, preferred way of doing the polymorphism in C++. However, that's only possible for it's possible, but it's difficult with the storage. For the storage, if you need to store kind of interface, we have to, for the concept, we have to choose either type erasure or variant or something like that, because we cannot store a concept or a template, because it might be multiple of them. And there are obviously many different ways, like functions, function design, etc. As pointed out before, there are a few ways of not doing it right, so I wanted to point out a few talks which are, in my opinion, very handy to know regarding the polymorphism. Inheritance is the base class of evil by Shimperan. Great talk about why not to apply inheritance and why type erasure is better. So, really desired talk. And we're talking about a lot of software engineering design practices, and most of them are applied to object-oriented design. But you can think about, C++ is not one paradigm language. You can do, that's the beauty of it, right? You can do a lot of things. So one of them will be a functional approach, and this talk from Scott is really really good in explaining what would be an equivalent of the functional programming for object-oriented approaches, which we are talking about here mainly. Like single principle would be a function. Dependency inversion would be a function as well, because in functional programming everything is a function. But you can also screw it up by not injecting it properly, right? Yeah, the idea is very simple. So if you think about the functional programming, everything is a function, and all the patterns are applied the same way. So that's pretty cool, and much easier to. The learning curve is much smaller if it comes to at least the patterns. One of the talks which I think it's very influential, it influenced me a lot personally, Andrei Alexandrescu, Design by Introspection, which allows to combine a lot of techniques, especially with the concepts and requires clause. So you can do if expert requires and verify that the member satisfy some concept or some that the object satisfies some concept which you want. That helps a lot with the templated kind of design, which is not necessarily required for a lot of applications, but it's very handy if you go for the template concept approach. So we don't have time to get into details of what's the best polymorphism for the best application and how to really approach it. We'll take a look into templated concepts because I think that's modern and exciting and way to go these days, but it's not for everyone. So proper abstraction depends on the project. Sometimes templated concepts are the way to go. Sometimes type eraser will be the way to go. Sometimes inheritance will be to go, especially with the like UI frameworks. That's often the case. I wouldn't like to claim here that there's any best solution. Like with anything, it depends. But combination of those might be also required in some applications. But I think it's important to know that having a loosely coupled design requires some sort of polymorphism because we want to apply the dependency inversion, and there are different ways of approaching that in C++, which is the beauty of it. So the templates and concept, if you know everything at compile time, meaning HFT, we know everything at compile time, high frequency trading for those who don't know what the shortcut is about. It's all about the performance, so most likely templates and concept will be the way to go in that case. Type erasure will be a case when we want to depend on some runtime dependency, meaning we read something from the file or something is unknown, we have some configuration, and we have to change the object, not only the data based on that. Inheritance, arguable never, might be exchanged with type erasure. It has drawbacks, as pointed out by Sean Parent, so maybe type erasure is the way to go instead, if the template and concept cannot be approached because of their drawbacks like compilation times and others. So quickly, let's take a look into the concepts. I'm not going to be describing much about how they look. I hope there are a lot of talks in that conference about them, so hopefully everyone can get the gist and maybe is even approaching them already in the code. So here we have a concept speaker, which requires the talk, which will return a void, and that's the definition of the concept. Notice that there is no inheritance required for the speaker implementation. So if you have regular speaker or awesome speaker or keynote speaker, all of them won't have to implement the iSpeaker interface and override the talk method like in virtual world. The only requirement is that the speaker will have to be having a talk, and that's much nicer from coupling perspective because sometimes it's difficult. You see the coupling sometimes when you have to include some files which you don't really want, and interfaces are sometimes the case where you can see that, because why would the regular speaker require to depend on iSpeaker? It's like iSpeaker is nothing really related to the speaker besides the interface. So then, when we have the talk, and that's one way of achieving this polymorphism and loosely coupled design, as pointed out, just one of the ways, not necessarily the best way, it's just a modern way of doing it. When we have the speaker here, it will be injected by the template. So the first, instead of speaker, usually you would write the type name here, or class, or abstract, whatever. Instead of that, we have something we will have to satisfy the speaker or attendee concept, and that will give us the ability to get better error messages from the callee side, not from the library side. Because if the template you provide doesn't have the talk, and that would bail out in somewhere in the code, instead of with the concepts, it will bail out on the instantiation point. So notice here, this design is quite flexible from testing perspective, because one, we inject the reference, so we can inject something from the test and still verify, like we can inject a mock or a fake or a stub into ACCU talk. It will have to have the talk method, which we can easily fake. And if it doesn't, it won't be satisfied. So all of that is really good. What we have to change is the wiring. The wiring is the part where we combine things together. Mainly in the main function, we have, like if you approach this design with the dependency injection, we often have the main where we construct all the objects, and with the DI, we'll just call, create an app, and all the dependencies will be injected and maintained appropriately. But if we do the manual DI, which is this case, we have the speaker. Notice here that we have the speaker concept of the speaker. That's the regular speaker, attendees. We have awesome attendees, obviously. And then we create the talk, and talk is going to be run, and that calls the speaker and attendees appropriately. So if we want to have, awesome speaker instead, we would be able to do that. If you want to have a fake speaker for testing, we could do that as well. So wiring is the separation, separates the creation logic from the business logic, which means that we don't have any, raw, new, make, unique, make, shared in the business logic. That's only the wiring part, basically in the main. If you think like whether on the factories or anything which is responsible for the creating the object, but it doesn't have the algorithm or the business logic in it. Because when you have the logic and you have make unique there or something like that, or the class itself, like ACCU talk would make, speaker, that would be really coupled as well, and that's not the way to go. And the composition route related to that is the unique location in application where modules are composed together, which means that you have the main, and that's where we, set up all the factories, set up all the DI, just, let's say, create me an app and run it. And main should be short and shouldn't have any magic in it, and, keep the raw ball rolling. So what about the dependency inversion principle? Is it flexible? Yes, it's loosely coupled. Why? Because we can inject different things. We can inject mocks, we can inject fake stubs. We're not coupled to the specific concrete implementations. Is it scalable? I would argue that it does. It is, because it applies etc. It's easier to change. When we have a new requirement from the product owner or anyone, and we have to change the software, we can easily change that by, if the product owner comes and say, I want to have, keynote speakers to do something else than the regular speaker when they talk, that would be easy to change. By not changing the whole thing, we can, just implement the keynote speakers. We just have to satisfy the interface or the concept, and then just inject it properly with the DI or manual DI or factories. Yes, it's also testable as well, because we can inject fakes and stubs and mocks and stuff. But, what is really important as well is that we can go too far, like with everything. Good design is easier to change than the bad design, which is the, moral of the stock. We can obviously go too far, and some examples where we go too far. When we have the speaker, we can, if you imagine that we have two methods, we can split it into two interfaces and just, split it into that small pieces, so small pieces that it doesn't make sense anymore because the responsibilities are too small in a sense. It's one responsibility but split into two. You can imagine that you can go too far with everything, and when you actually pay more tax on top of what you've done, and you can notice that by the fact that although you approach all these good designs and you have dependency injection and solid principles approach, but changing the requirement, it's still difficult because all the tests break all the time, and like they're really coupled to unit testing sometimes, and it's like changing the interface is difficult, and you change one test and 100 breaks, and the change is hard, meaning probably you've gone too far. Another way you can see that it's gone too far is when, for example, aiming for 100% coverage just for the sake of coverage. That's going too far, because it's often the case that when you have 80% coverage or 90% coverage, you don't change that much of the quality of the code, but try to achieve this last 10% or 5% is really difficult, and you go around the hoops and make the design even worse just in order to achieve this artificial coverage. So that's not great either. So going too far is a risk. And like with any approach, there are risks of going too far without much benefits. And we as a software engineers, we have to make the call. And I personally would make the call based on etc. Thinking if that design will be easier to change in the future or not. If I think it will be, or if I can claim that will be because of the experience or because of other factors, that's what I would decide for it. etc is always to the rescue. What about testing? So the last thing which we'll quickly talk about. As pointed out, all those issues might be kind of avoided if you properly follow the test-driven development or behavior-driven development. So in case of the ACCU talk, you can imagine that if you start from BDD, in that case, we can have the given when then requirement, which is often the case when we have the product owner, he can describe it in those terms, because the point is here that there will be English kind of requirements which we can easily apply afterwards in the code. So we have speaker attend this talk based on our requirements. Notice here that we used fakes. When I run the talk, I call talk run. Then I expect speaker to talk, and I expect the attendees to ask. So just to satisfy the requirement. And if you approach it from that perspective, if you start from there, you notice that we wouldn't create singletons on managers here, because why would we? That would be harder. It would be that's going too much just to satisfy the requirement and satisfy the test. And if you start from one test, then refactor, then another test, refactor, and if you just approach TDD the proper way, I think we'll get a really testable and easy design to follow. So BDD and TDD definitely will give us the loosely coupled code, in my opinion, because it will be really flexible. It will be scalable, because I personally think that the BDD and TDD drives easier to change design, because if it's hard to write tests, it's also hard to write the code. If it's easier to write the tests, we can quickly improve and change the design and requirements. Is it testable? Well, obviously it is. Otherwise, yeah, I don't know how to approach the BDD and TDD with bad testing, although I can imagine as everything that to be also screwed. So let's consider driving the code by writing the test first. And just a remark, what's the difference between BDD and TDD? Because there's also confusion about when you design software what you're supposed to do. I personally believe that it's really nice to have the requirements up front for the product owner and approach combine BDD with TDD. When you use the BDD to have automated example to guide us towards building the right thing, meaning we have the tests with the requirements, which we can try to satisfy with applying TDD for specific units of code which guides us toward building the right thing. And also it's important to know that tests are not only for verification, they are also for documentation. High-level tests are important, low-level tests are important. Neither is sufficient in my opinion. High-level tests are harder to figure out why they're failing, but they catch different issues than the low-level testing, which catch the small issues and are easier to figure out what's going on. So there are benefits, and I think we should all approach them as much as possible. So just to sum up, good practices are good practices for a reason. I'm here just a messenger, and I believe from experience that following a lot of those rules, if you follow them properly, and if you think about ETC in mind, having the ETC in mind, that easier to change design is the good design. We can gain a lot and not pay a lot of taxes for the future with the designs we make. So I think that's really important, and following those rules are a great way of trying to achieve that. Solid is much better than stupid. I hope that this talk kind of shown that. And Law of Demeter, which was the factor of that talk, as pointed out, it's all about those dots. We want to avoid them, and we want to inject the right things. We want to inject them in a loosely coupled way by injecting interfaces or something which is polymorphic. It promotes loosely coupled code, because if you inject the right thing on the right level, it's much easier to follow and change the code, which makes testing easier. TDD, BDD, single responsibility, dependency injection is a way to go, in my opinion, because that is if you just follow just those few things, we'll get really good design out of the box, in my opinion, which we can improve even further, applying more techniques and more understanding. But if you don't follow through with those, I probably will pay the tax in the future, and it will be hard to change and apply and satisfy the requirements that will come in the future. And yeah, we were talking about DI quite a bit, so I just wanted to point out that DI can be easily misused. It's all about the constructors, but it's all about what you inject into those guys. And the framework is definitely not required to approach DI. And you can do it many different ways with different ways of polymorphic, which is a great thing about C++, because there's no one best way of doing anything.